Dear students, today we discuss about the cantilever. What is cantilever? A cantilever is a beam fixed horizontally at one end and loaded at the other end. So it is a wooden scale. The one end or at the mid, the scale is fixed, so it is rigid. The other end is the free end. So this type of setting of scale or beam or any wooden material is known as cantilever. Let us derive the expression for the depression of a loaded end of a cantilever. So the cantilever is fixed at one end and it is free at one end. OA dash is a cantilever of length L. The length of the cantilever is L and loaded with weight W here at one end. Let OA dash is the cantilever at the position without without applying any weight here. Let OA, this is OA, is the position after the weight, the strain is given. That on applying weight or strain, so the position of A dash is reaches A, so it bends to a distance y. So the depression A dash A is taken as y. So that is a fixed end, this is a free end. The length of OA dash is L and on applying the weight is shifted to the position A. So the depression A dash A is y. Let us consider an element PQ here, the PQ of the beam of length dx at a distance QA. QA is taken as x from a loaded end. So the x distance from the loaded end. So the element is PQ at a distance x from loaded end, where C, it is the C, is the center of curvature of the PQ, the element PQ, and capital R is the radius of curvature of this element PQ. The load W at the free end and the force at Q constitute a external bending. So that the external bending moment is W into X, it is a weight into the distance X. We know that the internal bending moment already we have solved, Q by R into AK square is at the equilibrium position. At the equilibrium position, the external bending moment is always equal to internal bending moment. We know the internal bending moment is Q by R into AK square and the external bending moment is W into X, that is weight into distance X. On simplifying this equation, we get R is equal to QAK square by W into X. From the diagram, see here, from this diagram, the area dy, this is equal to x into d theta. dy is equal to x, that is this length is x. So the angle made by this is d theta. So this area dy is equal to x into d theta. See here. So dy, this area dy is equal to x into d theta. And the dx, this is dx is equal to r into d theta. Dx equal to r into d theta. So, from simplifying this, so d theta is equal to dx by r. Now substitute the value of d theta in the equation 3. So you get d theta equal to dx, and at the same time substitute the value of capital R. Already we have derived here. R is equal to qa square by w dot x. And substituting the value of R, we have d theta is equal to dx by qa square by w dot x. From this, d theta is equal to wx into dx by qa square. Now substitute the value of d theta in equation 3. On substituting, dy is equal to x into wx dx by qa square. On simplifying, we get w by qa square dx square dx. So the total depression on the cantilever of the length L. So y is equal to w by qa square integral 0 to L x square dx. On simplifying and integrating, we have x cube by 3. On substituting L, we have L cube by 3. So w L cube by 3qa square. So the total expression, the final expression for the total depression of a loaded end of the cantilever is solved as the depression y is equal to WL cube by 3qa square.